This is the first in my AI in Python series. In this video we're going to look at a Retrieval-Augmented Generation system, or RAG. If you don't know what that is, then you're in the right video, because I'm going to explain it. So we need Python, and then we start a virtual environment for the project. There are different tools for this, like Poetry and pipenv, but this is the built-in one. And then that creates a directory called ragenv, full of stuff, and we go source ragenv bin activate. Now we're using the virtual environment, so all the packages we install will be in that directory rather than in the operating system. Then we install a load of Langchain stuff. Langchain is a Python framework that lets you build applications powered by language models with tools for chaining projects, retrieving external data, and integrating memory. Basically, Langchain's a framework which wraps all the large language models, so you can just use one and swap out another, and you don't have to change your code. You can just change them in real time. So that's installed all the stuff that we need. Okay, now we want to open VS Code. So the question of AI is, how does meaning become math? How can we turn words or other human experiences like images or videos into something a computer can understand? In natural language processing, that's something called a vector. If you've done any kind of machine learning or data work before, you might have used NumPy or pandas. This is very similar. So to demonstrate, I'm using this Hugging Face embedding class from Langchain, along with a lightweight model called Mini-LM. This model was trained to represent text in a way that captures its meaning and content. Alright, so we import the class on this line, and then we load the model with this line. This loads the model for us, and we got the actual model when we did the pip install earlier. Now we create the vectors. In the first line, we're going to create a vector of the character A, and this embeds this text into a vector. What's a vector, you may ask? Well, just think of it as a list. So if you think of a Python list, imagine a Python list with loads of numbers in, loads of floats in, and it has, I'll print out the first 5 here, but there are actually 384 numbers in the list. And you could think of this like a spreadsheet. You can think of this like an Excel spreadsheet, OpenOffice Calc spreadsheet, LibreOffice Calc spreadsheet. You have columns, and then you can put items in the cells. And this is a bit like this. So this model stores text. It turns text into these vectors. It turns text into these numbers. And so I turned a single character into one of these vectors. I'm now also going to make a vector of a word, a vector of several words, a vector of a sentence, and a vector of a whole page, and then print them all out as well. And as you can see, we have the car vector again, which is a list of 384 items. Then we have a word vector, which is a list of 384 items, and then a sequence vector and a page vector. So you see, it doesn't matter how long the text is, it turns it into the same length group of numbers. It's 384 numbers. This is because it's how many numbers Mini-LM uses to describe the meaning of anything you give it. If you imagine the Excel spreadsheet and it has like column headers, the headers might be like the tone, the topic, the formality, the emotion, the tense, who knows, it could be, there's like 384 different features of that text, and it tracks kind of each of those features with a float. It kind of acts as like a semantic fingerprint for the text. It's like the semantic meaning. It's here, even the full page from a novel was converted in the same size vector. This is how the computer understands text. This is how the model, the Mini-LM, understands text. It understands language as a series of numbers. A bit like when you convert Python or C code to machine code, and incoherent, it seems to like to us an incoherent hex numbers or incoherent binary. This is exactly the same. The model was trained, and it decided that it could categorize text with these 384 dimensions. And what those dimensions are, we're not told, but it's decided that there's 384 dimensions, and it can like describe any text by changing the numbers on these 384 dimensions. If you don't understand this, it doesn't matter. Just think that we've converted the text into these vectors, into these lists of numbers. Now we can see that we can turn any sequence of any length into a vector. The next question is, how do we tell which sentences mean similar things? Or in other words, how does the AI use this to understand the text? Now we can turn any sequence. We can turn a text sequence of any length into one of these vectors. Now we can do that. The next question is, how does the AI use this to actually understand it? How does it use it as semantic meaning? How does it use it to do something useful for us? I'm going to show one example, which is called cosine similarity. You don't have to worry what that means right now. Let me walk through it. We use the same model as before. Now we define some sentences like I'm happy, I feel great, or I'm under arrest. Then we turn them into vectors. We can compute what's called the cosine similarity of these vectors. What this does, it makes a matrix of cosine similarity scores between every pair of vectors. And then we get the result out. Let me just press play. So the cosine similarity values range from -1 to 1, where 1 means identical, completely identical, same meaning. 0 means no relation, and -1 means opposite meaning. I'm happy and I feel great have the greatest cosine similarity. They're the same. They're basically the same. That has like a 0.5 similarity. Whereas I'm happy and I'm under arrest, well, it has some similarity. They both have I'm in it, or the word I, but otherwise they're completely different concepts, right? So I'm happy, you're happy, you're under arrest, usually really not very happy. So that has less semantic meaning. And I feel great and I'm under arrest, for some reason have a little bit more. Maybe it thinks it's sarcastic or something, but has a little bit more meaning. You know, if we say what's the threshold, let's say a threshold of 0.5 or above, then these two are the same, and then these two are different. What we as humans can understand very easily, but now the machine can understand it. That these two, as we expect, are very close, and the arm under arrest is very far from it. This is one example of how it can use the vectors. The core idea behind the vector search is that we don't need the exact keywords. It uses the meaning, and that's what semantic means, meaning, the meaning of it. By the computer understanding the meaning of it, it can then answer useful questions for us. So now let's scale up and let's do a whole book. I went to the Internet Archive and downloaded a book. The first one I came across was And There Were None by Agatha Christie, 1939. It's a mystery novel full of femme fatales using murder weapons, and that's the theme of our AI images that we have on here today. Joking about the fact that we're using AI. We grab the text from there. It's just an unstructured book. We will provide some structure, but if you have structured data like out of a database, then it can potentially work even better. But we are having unstructured data here, which is just a book I've downloaded from the Internet Archive. This is how you're going to be using AI in like work, unless you actually like work for an LLM company or something. You're likely to want to use AI based on that business's data, that business's own data, rather than like ChatGPT and like the big models which are trained on the entire internet. You're going to want to use your company's data or the data you're interested in the project. So we're going to use a model that uses this text, this book text, and then answers questions about this book text. We load that whole text file up into the memory as one long string, and then we chunk it up. As I said, if you had your own data, you might have database records, you might have a structure. You can do, say you've got like a product listing, could have, you know, any kind of document type text. There might be natural splits in there already, but just for this example, I'm just going to do kind of ruthless, just chunk them into 500 characters each. Not very sympathetic to the novel, but it'll work for this example. That we're just going to split at every 500 characters is going to be a chunk, to allow for the fact that that's not very sympathetic. Particularly, might not be very sympathetic. Split off in the middle of the sentence, and then it might not be able to connect one sentence to the other. I have an overlap of 50 characters. So this 50 character overlap gives the model some continuity between the chunks around the sentence boundaries. It knows and kind of read it as we'd expect. So that's the recursive character test splitter tool. I'm not going to have time to go through everything, so just accept it as magic spells or just see what the code does. You don't have to understand everything. I can buy a plane ticket and use a plane without understanding exactly how a plane engine works. And this is a high-level framework on purpose. It's a high-level framework to allow you to get on and use LLMs. So anyway, we have this document objects from Langchain. This allows Langchain to track metadata on it, like where it came in the book. Then this is where the magic happens. We take each chunk and embed it using mini LM, just like we did with the earlier sentences, but now hundreds of times. It's going to go through the whole thing and sort it out. Then we use this thing called FACE. Facebook AI Similarity Search is a library for efficient similarity search and clustering of dense vectors. It contains algorithms that search in vectors of any size, up to ones that possibly do not fit in RAM. It also includes supporting code for evaluation and parameter tuning. Basically, we're just going to use this as a vector store to store all our vectors in. We've split it into chunks, and we've added each chunk as one of these documents. And then we have added them all to this vector DB, this vector store, and then we save it. So when we run this, it's taken each of the chunks of our novel, 500 character chunks of our novels, has been turned into vectors, which are then stored in the vector store. And now we have a directory called ChristyDB, which has this vector store in it and some metadata. So this vector store is a bit like, is a binary database. So a bit like SQLite or Berkeley DB. It's a file on the system, but it's a database of all these vectors. It's create the database and we saved it to the disk, so it doesn't have to re-embed the book each time. What this has done is built an index which has let us search these chunks by meaning, not keywords. So this step has turned the novel into a machine-readable knowledge base. That's what lets the AI can answer questions like, what's the sequence of events, or who are the characters, or whatever we want to ask. I'm pretty happy with this, that it generated the bear clock. So all these femme fatales are Agatha, trying to be Agatha Christie characters, and one of the characters gets murdered with a, spoiler alert, gets murdered with a bear clock. A clock in the shape of a bear. So now we've embedded the entire novel and saved it as a vector database. We can start asking real questions in plain English and get useful informed answers. We're going to start with this question. Who lives and who dies in the story? This is a great question because the answer is scattered across the whole book. It's not something you'd find on one page. It's not something you could easily answer, with more traditional tools. So we load the model again, and we load our database that we just made. This line performs the semantic search. It embeds the query, compares every chunk in the FAISS index, and pulls out the most 12 relevant chunks, the ones that have most meaning relation to our question. We have a question, who lives and who dies in the story, and we want the 12 chunks in the story that have most relevance to that. So it'll do a similarity search, just like we did earlier, and find out which chunks are the most relevant to our story. Again, we're using this mini LM model. When you're doing things in development, it's quite nice just to have everything that runs locally. It's very easy to make unit tests and so on when it runs locally. One could load ChatGPT model, and then you'd have to make sure that your API key was in the environment. That will actually run up money and run up costs. The API of ChatGPT costs money. That's why I'm using this open source small model, and it works really well. So we're going to run this script, and it's going to give us the 12 most relevant chunks of the book. Great. So here we go. As we did in our code, top relevant chunks. There it is. Print chunk I. So we got chunk 1. That she died as a neglect on their part says that sort of thing. It's quite impossible to prove. So it has the word died in it. And then somebody was hanged. Emily Brent, Vera Claythorpe, all the femme fatales in it. Somebody's dead. Next chunk. Some potassium cyanide. A lot of strong female characters who then die. Miss Gabrielle Turl, Miss Brady, Vera gone rather white. Anyway, we have some chunks that are kind of to do with life and death. This is the retrieve phrase. We've retrieved chunks of data. So before we set up in the setup, we parsed the data, and now we retrieved some chunks. So the R in RAG is retrieve, and we have retrieved some chunks from the novel. Now we've embedded the whole novel, saved it as a vector database, and then we get chunks out of it. This is the first step. So this is what we did, same as we did before. So if you ever use like map reduce or map filter, there's a lot of kind of similarities to some other kind of, tech that's been around. But the way it works is that we have two models that are friends, right? So we start by retrieving the top K chunks. So I did 12 in my case. We then assemble that together, basically. We augment the LLM. So the LLM, so we have two. We have the first one, which is getting the chunks, and then the second one, which is then answering the question. So we're kind of assembling, we're retrieving the chunks, we're assembling them together, and then augmenting the generation that the LLM is going to do. We have our question, who lives and who dies in the story. We then read our database. We get our 12 chunks. So we've used the mini LM model, but now we use another model. So we're using the model Mistral running locally via a lemma. Again, you could use ChatGPT here, but I like to use a local model when I'm just mucking about and potting about. We feed the model the 12 chunks that we have. So this is the prompt that we want it to generate from, and we're augmenting it with this context, with our 12 chunks that we've got out of the vector store. So instead of using any information from the web, it just uses the context that we provide, the retrieved context that we provide. We retrieve the context from our data in these chunks. We then give it to the LLM, augment the LLM, which can then generate the response. We get to here where the model generates a response using our book's relevant excerpts. So it's not guessing or hallucinating based on training data. So if we run that, what we just did was we used vector search to find relevant passages. We fed those to local LLM, and we got back a reasoned answer grounded in the book. So the answer says, in the given excerpts from a murder mystery novel, it appears that 10 people are involved in the story. However, their fate is not explicitly stated throughout these passages. The characters we know to be dead are Marston, Mrs. Rogers, MacArthur, Rogers, Emily Brent, Armstrong, who's said to be dead, Lombard, shot and found near Armstrong's body, and Vera Claythorne. Blore and the assistant commissioner are still alive at this point when these excerpts end. The identities of the other characters, such as Miss Gabrielle Turl or Miss Brady, remain unclear regarding their fate in the story. Just like that, we've built a system that can read a novel, search for meaning, and answer questions with the supporting evidence. Possibly because it's such a long book. Possibly because of, it's a novel, quite a long piece of text. Maybe we needed more than 12 excerpts for it to know everything what happened to the characters, but that's a pretty good summary. So far, we've shown that our language model can read a book, understand a question, and generate a freeform answer. But now we want structured information. So when you're making something for a company or for a project, you're probably going to want it connected to other systems. That's the point of using a programmer rather than just typing it into the ChatGPT prompt. So now we want structured information. We don't want just a freeform answer. We want structured information. What I want is a list of who lives and dies in machine readable form. This time I'm going to ask the LLM for structured JSON format. So I'm going to give it the context, my excerpts, and I'm going to say, please format your answer like this. Character, the name, the status, if they're alive or dead, the cause of their death. So this is the same LLM as before. Everything's the same as before. It's just being prompted in a different way. And then we're going to parse the JSON output, and hopefully it will be valid JSON output. If it works, we're going to loop through the results and print them nicely. And if it fails, we're going to go back to showing the raw text. Let's see how it runs. Okay, and it's finished, and it's really good. Look at this. Isn't this beautiful? Mr. Justice Walgrave dead. well, not beautiful, Mr. Justice Rawgrave, just read dead, poisoned with potassium cyanide. Emily Brent, alive, not mentioned to have died. Mr. Rogers, dead, poisoned with the potassium cyanide. MacArthur, dead, not specified, but mentioned the order of deaths. Rogers, dead, poisoned with the potassium cyanide. The crushed by the heavy marble clock. There we go. That's the clock in the shape of a bear. Miss Brady died of natural causes during a storm. So, if I increase the level, decrease the number of snippets, it will solve a few of these things. But there we go. That's really good. That's really good. We could plot this, store it, turn it into a graph, do further processing on it. So instead of getting the plain English answer, we've got JSON. So this is really powerful. It turns unstructured fiction into structured data. And we didn't have to write like a parser or a knowledge graph. We just asked the models to do it, and it gave it the right context. So with the structure, we could ask other questions like build a timeline of deaths, or visualize their character arcs, or ask it to have a list of scenes or a list of settings. But all this comes from just a plain text novel and a few lines of code. It's amazing. So let's look at what we've done. So we've got a query, who lives and who dies, and we've retrieved the chunks from our vector DB, our vector store. We assemble it together, and we augment the query to the LLM, and then the LLM generates an answer in text or JSON. Now we've been through these 6 code samples, hopefully you can understand what RAG is. So we pre-processed the text, we chunked it into 500 character segments, and then turned each one into a 364 dimension vector. We then stored them in the FISSS vector database. We then queried the content, which then pulled the top 12 semantically relevant chunks. And this then can assist the second LLM, because we augment the second LLM with the retrieved context. So it can then generate the answer and format the output into a human or structured response. So the model doesn't have to remember the whole book, because we feed it the relevant parts that we wanted to give it. And we can apply this to anything: books, manuals, transcripts, documentations, emails, code bases, business data. RAG, Retrieval-Augmented Generation, is a technique that helps the large language models work with custom or private information, stuff that isn't the training data. If you ask a language model who dies in and there are none, it will have to guess based on what's learned during training. If it wasn't in the data set, it can't reliably answer. And in business, a lot of the stuff is private data. So, private data, private documents, it's not going to be in like ChatGPT's public models. So you have to feed it into the LLM. And RAG is a way to feed it in. There we go. We got to the end. Thanks for listening. Next video is going to look at validating the data that comes out of LLM with Pydantic AI. That's going to be very exciting. So thanks for coming, and love you. Bye.